Radioactive decay can be modeled by the function A of t times c times e to the kt, where c is the starting mass, k is the relative growth, t is the time elapsed, and a is the mass of the radioactive component remaining. Part A, the half-life of the radioactive material cesium-137 is 30 years. Suppose we begin with a 100 milligram sample. Find the relative growth. So for part A, we're given that the half-life is 30 years, which is T. The starting mass is 100 milligrams, which is C. And A, which is the remaining component, is 50. And we find this 50 by dividing 100, which is the starting mass, by 2, since we're finding the half-life. From there, we just plug in into the equation that they're given. So A of T is 50 is equal to 100 milligrams for C, E to the 30, which is the time, and K, which is what we're looking for. So from there, we divide 100 by both sides, and we get 50 over 100 is equal to E to the 30 times K. And in order to solve this problem, we need to find the natural log of both sides, and we get ln 50 over 100 is equal to ln E to the 30K. The 30K becomes the coefficient, and since ln E is equal to 1, we're just left with 30K is equal to ln 50 over 100. And by dividing 30 by both sides, we are left with K, which is negative 0.0231. Part B. At what rate is the mass decreasing in milligrams per year after 50 years? So for this, we are going to need the answer that we got from part A. First, we're going to plug in 50 into the original equation for A. So it's going to be 100 e to the negative 0.0231 times 50 for t. And we get 31.5058. To find the rate, we're going to then find A prime of t. And we're going to multiply k times A of 50. And that's 31.5058, the one we just found. So A prime of 50 is equal to negative 0.0231 times 31.5058, which is equal to negative 0.7278. Therefore, after 50 years, cesium-137 is decreasing at a rate of 0.7278 milligrams per year.